I'm going to give you kind of an overview of the work that we have been doing in biorefineries over the last 10 years, starting in the University of Aachen, and then I continue with my firm, giving external support to people in Forschungszentrum Jülich in Germany, and also in a center is called Bioeconomy Center in Germany too. So we look for projects and we continue developing concepts in the area of biorefineries. So first of all, well, I think this is not needed anymore because I already have been introduced to you. Just to comment a bit on the projects that I'm going to talk to you in this presentation. We are going to discuss a bit the things that we are doing in biorefineries since, well, 2014 with my firm, 2009 since I was working at the University of Aachen, and also a little bit of the new project of interfaces, new European project we have started this year, and some of the PhD students that are involved in these projects are also present in this audience. So I greet them from here. So I always like to present or to talk about biorefineries. I always like to start with this slide, asking you kind of a question, which is, let's imagine that we have an investor that is coming from the door and says, you have all the funding that you need. No, money is not the issue. And I want you to build a petroleum-free biorefinery, which can be a business for me. So I'm an investor, I'm going to put all the money you need, but at the end of the research, what they want is to have a company working on that. So we need to start to think what to do with the money. And this is something that is a very useful question for many things, in the sense that we are usually constrained in our brain by the money. We don't dare to do things because we think we don't have the resources, we don't have the money to do this. But now the question is different. What if you have the money? What would you do with this? Money is not the problem. So we need to think where to put the efforts and the research to create, in, say, 3, 4, 5 years of research, a biorefinery concept that can be petroleum free, and we can sell to this investor that is giving us the funding. So the main question is where to start. So when we started to work with my group in Aachen, I designed 3 kind of main lines of research that are important for biorefineries. The first line is the use of solvents. We will need solvents because we intend to convert a raw material, a substrate, A, in a product, B or C. And for this, in many cases, we are going to need a solvent to make the process. In some cases, we will be lucky and we will be able to set up a solvent-free process, and we will see some cases in this presentation. But normally, what we are going to need is a solvent to do the things. And since we are working on petroleum-free biorefinery, we will need to put a focus on bio-based solvents. This is obvious, I think. So some of them, that the ones that we have, we are going to see some of them in this presentation, is the use of two MTHF, dibutyltic solvents. This, and we have other emerging ones which are starting to be used in biorefineries and in chemistry in general too. So the first axis is solvents. We need to think in them, in the way to create and to use them. The second important line to think in biorefineries is water. And this is because of some reasons. One of them is that all forms of biomass in this planet contain water. So if we want to make chemicals and products out of the biomass, we need to find a way to treat on or to deal with this water. We need to learn when we are going to get out of the water, whether or not we are going to make a process in water or in water-free systems. And all these things will need to be integrated in the process plant. But probably more important than this is that we are living in a planet in which we are starting to have problems with water in many places. So we need to find a smart way and holistic way to reuse and to manage the water in a sustainable way. So in this presentation, we are going to see some concepts on seawater, and we are going to see some concepts on how to recycle the water that we are using in a plant, which, as we are going to see, is quite a lot. It's a huge volume of water we are going to use. So this is why this is so important to put efforts in this line too. And the third axis that we have that is important to think in a biorefinery is catalysis. ideally, we would like to have a process in which we don't need a catalyst to make the process. We are going to see one example in this presentation in which we were lucky and this is not needed. But usually, we will need a catalyst to convert a compound A in a product B. If we want to think in terms of sustainable bio and so on, we will need to think in enzymes and also biogenic catalysts that we can create in nature and we can make them to use in biorefineries. So starting from the solvents, one of the solvents that we are going to use in these presentations is MTHF, which is this structure that we have here, which is quite interesting in the sense that we can make from biomass, from glucose, levulinic acid, or pulp from xylose, and then we can convert it, and we can use it in organic synthesis, in biorefineries, biocatalysis. And interestingly, when this is in the milieu, in the environment, the solar light and the air is going to open the ring in a reasonable amount of time, and then this carbon is going to be integrated once again in life cycle. So this is an emerging solvent from the last year. It has been already started to bring quite a lot of uses in organic synthesis and biocatalysis. Here is the first review paper we published with Andres Alcantara, which is in the audience, about this. And very recently, also 2 years ago, we published kind of update of this because the uses of these solvents are increasing. An important point if we want to think in a solvent is, can we reuse it? Can we recycle it? In this case, MTHF bring us quite useful miscibility gap with water because we can make a distillation at 60 degrees in a straightforward manner. So there is a way to recover and separate the MTHF from the water and use it again in the plant. The second kind of solvents that we are going to see in these presentations is this. I don't know if you are aware of this type of solvents. One thing that I forgot, I don't mind if you have any doubt or question or something, you can ask or you can wait for the end. This is it's not an issue for me. If you have a question, just interrupt me and you can ask a question. So these are kind of solvents that are quite strange at the beginning because one mix two solid stuff and then you get a liquid. Sounds kind of counterintuitive if you want to put it in this way. The prototypical example of this is a mixture of choline chloride, which has a melting point of more than 300 degrees, and urea, which has a melting point of 133 degrees. If we mix 1 mole with 2 mole of this one, we get a liquid at room temperature with melting point of 12 degrees. The urea is distorting the crystalline structure of the choline chloride, and this is making the disruption of the crystal and making a liquid at room temperature. So years ago, we started to work in this because we got fascinated with this idea. And we thought, okay, we have quite a lot of groups that could distort this crystalline structure of choline chloride in nature. We could use alcohols, we could use amines, we could use carboxylic acids, sugars, polyols. So then we thought, okay, this field is really impressive because we can start to create quite a lot of bio-based solvents with different properties just by thinking in a mixture of choline chloride with different molecules that we can get in nature. And in fact, it works quite well for many of them, and you can really create an array of new solvents, which can find a use for many areas because they have different properties. For instance, in some cases, you even might have chiral solvents, which can be used for some kind of applications. So DES and MTHF are the two biogenic solvents that we are going to see in these presentations, but of course there are others that we can make use of in biorefineries. So the next point to consider is the water and how can we integrate this in a biorefinery. I always like to put this example because I think it's quite, it gives a clear vision on the problem that we have at this moment. Let's imagine that we want to set a continental flight, which is 12 hours, 10,000 kilometers, with then Airbus 340. This is going to have an impact that we can count it or can determine, which is 100,000 liters of fuel. In the case of planes, it's kerosene, and this is not it's not by a coincidence. It's because we need to find a fuel that can get frozen at the altitude in which the plane is flying. So the external temperature where a plane is flying is in the range of minus 50 degrees. So you need to have kind of a blend solvent which do not get frozen at these conditions, and this is why it's kerosene. So, and this is petroleum, of course. So this 100,000 liters of fuel are coming from refineries from oil. So now we are quite ambitious and want to set a petroleum-free biorefinery. So we are entitled to make this from wood. That's the point. So there are some initiatives in which they are working with the glucose that you get in the cellulose, and even with the pentoses, with the xylose from the hemicellulose. You do fermentation and you make the farnesene, which is a terpene that can be hydrogenated, and you get kind of a jet fuel-like type. That there are some proofs on planes, and in principle you can replace the kerosene by that. But now we have to think in numbers. And in numbers is the first step in biorefineries is what is called pretreatment. We are going to see quite a lot of this in this presentation. We need to make the pretreatment to make the separation of the lignin, the hemicellulose, and cellulose, the three main components of lignocellulose. And to do so, we need to put the lignocellulose in water and make an acidic process or basic process, depends on which one we want to use. And the problem is that this is solid. So the biggest amount of lignocellulose that we can put in a water without starting to have problems of stirring is in the range of 100, 150, maybe 200 grams liter of lignocellulose in water. And that means that if we do the things well, the amount of fuel that we can produce by this amount of water is more or less 100 milliliters. That means that to keep one Airbus for one continental flight, we need 1 million liters of water. And this is only for the first step. Yeah, you still will need to go back to your homeland in another continental flight. So it's another 1 million liters of water that you have to add to the bill. So this is the issue that we have. So we need to think in ways to make the valorization of the lignocellulose, but thinking in the water and try to find ways to use non-edible water sources and especially recycle the water that we are using. We have to design clean processes that allow the reusability of the water if we really want to have a sustainable case in biorefineries. One option that we thought in the past is, okay, for these cities that are living at the seaside, for algae-based biorefineries, why don't we use seawater as a media for biorefineries? It's something that can work well for this kind of cases, especially, and very important, if the processes that we envision are clean, are bio-based processes that lead to a manageable waste seawater, in the way that we can treat it in an easy, straightforward, and cheap way before we put it back to the sea. That's very important. But if we manage to get this, probably we can have an option to alleviate a bit the problem that we are having with the water. So we did some work in the past on this area. So I think we were the first ones to show that the commercial cellulases can work in seawater. So we are used, when you start to work with the enzymes, you are used to buy it in Sigma or in wherever, and then you look in the bottle and says you have to work with this enzyme in pH 4 in a buffer in a temperature of this and so on. This is great. This is the way of making the characterization of the enzymes. But if we are thinking in terms of real life, we need to get the enzymes to be trained to work in real conditions. And real conditions in biorefinery probably are going to be crude effluents with a lot of impurities, with a lot of osmotic or ionic strength of ions and so on. And we have to see if this is working in these conditions. So the first thing is that we did was we took a real seawater sample. We took it from the beach. We went to the lab and put these cellulases to work in this system. And the first thing that we realized was that the accelerase, which was the cellulase, the commercial one that we were using, was converting the cellulose in glucose more or less in the same ranges as in the real conditions of the bottle, which was said. So it was working quite well. So then we decided to make a step forward, and the step forward was, okay, if we have a desalination plant, which is quite useful in many places in the world because we need the water for drinking, we are going to have a kind of a brine as a waste. It's the concentrated seawater that we have. Why don't we use this as a reaction media for that? And we realized that in two-fold concentrated seawater, the enzyme still was working, but a little bit less than with the pure seawater. And when we started to make the concentration, we realized that the enzyme started to have problems, which is normal because ionic strength is quite high. But we have the solutions in these days for this. From that sense, or in this sense, we are in the safe side. And one is try to design enzymes to make them to work in the real conditions that we are working. So we continue working in this area, and then we took a cellulase and tried to evolve it to work in seawater, concentrated seawater, and also in aqueous solutions of biotecnologic solvents. The reason is that if you make the pretreatment of lignocellulose with ionic liquids or with biotecnologic solvents, most probably you are going to have rest of the ions in this system, the water effluent that you want to have. So it's better to train these enzymes to work in this because most probably they will find this in the subsequent process. And we managed to find one variant that was able to work in a better form in the three-fold concentrated seawater. So if we have had a case for continuing, probably we have been able to develop a new variant that was able to work in these conditions properly. So as lessons for this part, we need to think, or we need to look for water systems that cannot compete with food industry or food, in this sense. And we have to find a way to design the enzymes to work in these conditions. And this is what we did in these cases. So, as I said before, the first step in a biorefinery is always what is called pretreatment. Lignocellulose is contained at the most by three main components, which is lignin, which is a kind of aromatic polymer. It contains the so-called hemicellulose, which at the most is xylose, pentoses with some other sugars, and it's an amorphous fraction. And we have the famous cellulose, which is crystalline, and is containing also a big part of it. So the first step is try to find a way to make the separation of these three main components, to start to make chemicals, to make products out of them. One option that is typically used is sulfuric acid. Sulfuric acid is fantastic. You don't need to think in the type of biomass. You don't need to think in anything because it's going to destroy everything. So you put the sulfuric acid in the biomass, you make it disentanglement, and you get part of lignin, degraded but lignin, and you have a soup of sugars containing from the hemicellulose and cellulose all together, which if you have a microorganism that can work with pentoses and hexoses, you can go in fermentation to make something. So it's quite efficient, it's quite cheap, but it has some issues associated, and those are the ones that we have here. It's corrosive. We might have the risk of explosion risk, especially in contact with water, or if you have moisture or something. You have to recover it from the system, and you are going to generate a waste for that, which in terms of a large volume plant is going to be an issue. The handling and the storage of the sulfuric acid is not easy, I have to say. And then this make us question whether the use of sulfuric acid is sustainable. Of course, if you use lignocellulose, one can claim that this is sustainable, but the overall picture is more discussable, we could say. So now the question is how to compete or how to overcome the sulfuric acid. And you cannot compete with sulfuric acid by simply replacing it by other things, because it's very cheap. So no one is going to believe you if you say, no, this is better. No, this is not better because it's more expensive than the sulfuric acid. So the way to solve this problem is to trying to generate more value out of the things that you are doing. This is what we have here. So in this case, you make an investment. We are going to use a catalysis system that is going to be more expensive than using sulfuric acid, but we are going to get purer fractions, cleaner fractions. We are going to separate the fractions, and then probably we are going to get a market for the three things. So at the very end, we are going to generate more value. This is the main lesson that we have to keep is you cannot compete with a very cheap thing just by changing. You need to think in something that is going to generate more value. So an investor should see this as an investment, precisely, and not as a waste of money that you are putting in a system. So how to handle that? Well, this the field of the pretreatment is a very huge one in biorefineries. There are quite a lot of studies. Also, industries are working quite a lot on this. This is a paper we did years ago, considering which were the trends on pretreatment at the industrial level by looking at the patents that industries were providing. And our conclusion was kind of to reinforcing what we were looking was that we wanted to have a pretreatment that could use only bio-based resources. At the very end, we want to sell or to put forth a petroleum-free biorefinery. And this is going to include the solvents and catalysts. We need to have a process that is not going to degrade the fractions that we are using. Of course, it has to be effective in terms of cost. Otherwise, no one is going to use it. It has to be scalable if we want to make it huge. And very important, at least for us, it has to be clean and it has to enable the reuse of water and solvents because of the things that we have seen before. So years ago, we started to work with a new concept that we call the Organocat process. And the idea was to make the selective separation of the xylose from the hemicellulose, lignin, and cellulose in one pot in a biogenic form. The concept is the one that we have here. So basically, it's a biphasic system with water and MTHF as a biogenic solvent. And we are going to use oxalic acid as a catalyst, which is a biogenic acid that can be generated, for instance, in fermentation. We are going to keep a temperature of this system up to 140 degrees. Typically, we use 135, 140. The reason is that temperatures higher than 140, the sugars start to get dehydrated to form furans, and something that we don't want because it's an impurity. So we have to keep the conditions under this temperature to be sure that this is going to be kept under control. So we put this at the beginning, we used to put for 6 hours. We are doing now with all the optimized things in 90 minutes, more or less. So in a soccer match time, more or less, we could say, we can process 100 grams liter of lignocellulose is what we put here. So then what is going to happen in these conditions? What is going to happen is that at 140 degrees, oxalic acid is strong enough to make the polymerization of the hemicellulose because it's amorphous and can enter well in this polysaccharide, but it's not strong enough to depolymerize the crystalline cellulose. That means that we are going to break only the hemicellulose, and we are going to make the separation of lignin. Hemicellulose is going to be converted in the sugars, xylose, and the cellulose pulp is going to remain crystalline as a suspension. Lignin is going to be in situ extracted to the second phase, and we can get it in distillation to get the lignin. The pulp infiltration, we can get it and we can put in contact with the cellulases to get the glucose. And we have the sugars that are coming from the hemicellulose, xylose at the most. And we found that we could make the recrystallization of the oxalic acid to put it back in the system. So in one pot, using entirely biogenic resources, we can make the separation of the three main fractions of lignocellulose. In reality, this is thing like we see here. This is the cellulosic pulp. This is the water, and this is the MTHF phase with the lignin, which is extracted. We get the cellulose, and we get the pulp that we can put in contact with cellulases, and we realize that the ranges of cellulose production were more or less in the range as for commercial cellulose, which is giving the hint that the accessibility of the cellulases to this pulp is adequate. So we also thought, okay, how can we improve this? And one way to improve this is trying to increase the amount of lignocellulose that we can put in this system. The problem, as I said before, is that we can put 100 grams liter of lignocellulose. It's a solid stuff. If we charge more than that, we are going to have the issue of the steering, and we are going to have quite a lot of mass transfer issues and so on, and this is not going to work properly. So we thought in this concept, just for a lab concept, to make the proof of principle that we can process and recycle the water and the solvent with this system. We started with 100 grams liter. We make this Organocat process, and we filter the cellulose pulp. Once we filter this, we can add, once again, 100 grams liter of lignocellulose. But we make a second cycle, then we filter the cellulose pulp, which is the solid that is remaining, and we add another batch of 100 grams liter. Working in these conditions, a proof of concept in the lab, we managed to process 400 grams liter of food per liter, which is starting to be quite an interesting stuff, because the sugars that we are making in the water, the xylose, are starting to be in the range of 100 grams liter, which is the range of the concentration of sugars that you get in industrial processes in fermentation. So probably you could even get this system to the fermentation without any downstream processing. And we show that we can recycle the solvent and the water with this system. So we got some engineers in the team, and then they were quite eager to start to make some numbers to realize where we are. The optimized process are the black columns that we have here. So here is the investment that we have to make in capital cost, in the energy that we put in the system, the cost of the lignocellulose. Even if it is regarded as a waste, it's not actually a waste. You have to pay for, and this is the price that you pay for. This is the money that you would earn by the fractions that you are selling. And good news in principle, on paper, I have to say, we are very far from process at this moment. But on paper, we see that we could earn money with this system. The most important thing is that we can be numbers as long as we get a market for the three fractions. We need to get a market for the lignin, we need to get a market for the xylose, and we need to get a market for the cellulose. If we get a market for the three fractions, we might be numbers. At the moment that one of the three fractions is not commercialized, this will be lower, and then we will go to this negative part. So the important thing is that if we want a biorefinery to fly, we need to valorize any carbon that we get there. If we lose carbons, we will not be numbers. That's a point that we have and we need to consider here. We also work in extending this concept to other sources of biomass. And well, I don't think that I have to give an introduction of the yerba mate to you at this moment, to Uruguayan people, but just to say that this is a raw material that is consumed quite a lot. I also drink quite a lot of mate, and then once this is washed and exhausted, I was thinking, okay, now this is a waste. It's not the food anymore because it's already consumed. Why don't we get a value out of this? And then we made the Organocat process with this, and we realized that we can get xylose from mate, very close to the values that we get in literature for the mate. We can get the lignin of mate, which is also quite close to the values, and we can get the pulp. We also have made this with other kind of plants in a bigger project in Aachen, working in perennial plants. And the idea is to make a kind of a synergy on the lands that are not being used for food at this moment. We are trying to revalorize this now again for using in perennial plants to make the raw materials for chemical industry. It has been a very interesting project because we also have included people which are working in agricultural research and land use, which are fields that are very, very far from the things that I know. And attending this kind of meetings is very interesting because you learn quite a lot of things from these people. So I think it was quite worth project. Also, we got this contact in Malaysia, and they were interested in valorizing these empty fruit bunches from the palm oil industry. You have the seeds here from which you get the palm oil, and you get this as a residue of it. So they ship us a sample of this EFB to see if it was possible to make the valorization of this. So we put to work the Organocat process. It worked quite well, and this is a pulp which is accessible to the cellulases that we get once we made the process. More recently, this year, we have started to understand a bit which are the structural patterns that we have in lignocellulose for the Organocat process. It's a very new paper that has just now appeared, in which we made a study on different biomasses considering the lignin, pulp, and sugar yields, which are the conditions that are best, and then trying to make an estimation on which are the best conditions or which are the parameters that are better for anacidic pretreatment than the others. So this is a very new line of research. It's the first paper of this set, and we hope that we will provide more on this in the next years. Scale up, we also did some experiments to put in 3-liter scale. This is the reactor, this is the biomass, this is the water, and this is the organic phase. We put it with silicon in this reactor, 3 liters, and it worked also quite well. So in principle, you are able to make the scale of this process. Another important thing is that we had the team of engineers that are eager to see a bit how this was working, and they have started to design the pilot plant of Organocat. And this slide is just to illustrate that the process can look like quite simple in the lab, but once you try to make a scale up of it, this starts to get quite complicated. And this is illustrated in that this small reactor that we have here lost in this constellation of a lot of wires and filters and so on, this is actually the Organocat reactor only. The rest is downstream processing. This is the downstream processing to recover and recycle the solvent, and this is the downstream processing to put the cellulases to work to get glucose out to cellulose. But the process in which you make the separation is just this small reactor that we have here. We have started to work also in the new version of the Organocat, which came by a problem that we saw. The problem is that the oxalic acid works well, but we saw some decomposition at 140 degrees over the cycles that we are using. So we need to find a new catalyst, and the considerations that we put, of course, are that it must be biogenic. We need to recycle it. Of course, it needs to be stable at this temperature, cheap enough, and it has to be strong enough to make the process to work, but we have to be able to control it to avoid that the cellulose is intact when the hemicellulose is being degraded. So we went back to the wood, is from the place from we tried to get all the things, and we put the eyes on this FECA. FECA is famous now because it's starting to be one of the monomers that is believed to be the future of the bottled plastics. Coca-Cola and some other companies have at this moment a joint venture trying to find new polymers for the bottles. But this is also an acid, the acid molecule. So we thought, why don't we use it as a catalyst in our system to see if it's working? Because it would be great, because we know that this FECA is going to be in bulk scale in the future. Well, it works quite well, we have to say. So this is the first concept that we published 2 years ago. And interestingly is that the acidity is quite in the range that we need to use for that. The solubility in water is quite appealing for us because at room temperature is almost insoluble, but it starts to be quite a lot of dissolved at 150 degrees. That means that we can heat the reactor, make the pretreatment, and then when you cool it down, it goes just a crystal again and you can recover it. And important point that we are working at this moment is that the type of the lignins that we get, depending on the process conditions, are different. That gives us a hint that probably by changing a little bit the reactions conditions in the pretreatment, we will be able to produce not only one lignin, but some types that can be used for different markets or different uses. So we're working on this now. Okay, now we need to make or generate a bit of value from the things that we are doing. One important compound that we can make is fufura, that is made from the cellulose that we produce in the Organocat process. So this is the Organocat process. We put the beechwood, the lignocellulose with oxalic acid. We get the cellulose, we get the lignin, and then we put it. We use this aqueous solution with the cellulose that was coming from the hemicellulose, and we realized that by using a mixture of sodium chloride and iron chloride in a two-phase system, by heating up 140 degrees again, we are able to make the dehydration of the cellulose to get furfural, which is coming to the second phase, to the MTHF, and then we can get it from the system. The system resulted to be quite stable, so we can recycle this water fraction for a number of cycles without any loss of the activity of the catalyst, which is claiming probably for a continuous process in the future. So we are starting to have a furfural. Furfural is interesting because it has a market price in the range of €1 kilo. So we are starting to get part of the fractions that we are doing. We are starting to get into something that is valuable in the market. And I can tell you all the nylon that was being done in this, being made in this planet before the petroleum time was coming from furfural. Then petroleum is cheaper and this was abandoned. But most probably in the future, probably we will find new polymers from this furfural raw material. Another component that is interesting is the HMF, hydroxymethyl furfural, which is obtained from the glucose. This is tricky in the sense that we cannot, or it's very challenging to make it from glucose because the glucose molecule is very stable. It's better to make it from the fructose because it's not that stable and we can process this better. So we envisage a process in which, first of all, we get the glucose from the cellulases, from the cellulose, from the lignocellulose, and we use a immobilized glucose isomerase to make the 1,1 process, the fructose syrup that is used in food industry, which leads to 1,1 glucose fructose as an equilibrium pattern. We filtered this enzyme and then we got this mixture with the oxalic acid seawater system, MTHF as a second phase. We heat it and then we get the MTHF that is being extracted once again in the second phase. We solve the problem of water in the sense that the HMF is in the organic phase, so we can process this in fire chemistry in organic solvents and not in water if we want that. Of course, we can recycle the oxalic acid by recrystallization of it, as we saw before. And then we wanted to test whether this enzyme was stable in these conditions, because we are going to have a kind of a recirculation system here. So the question was whether the glucose isomerase immobilized was stable in the mixture of glucose, 50% with more or less 5% of MTHF in seawater. We were quite happy to see that this enzyme is very stable in these conditions, so we can process it for quite a lot of cycles. And of course, this concept also is working quite well in the synthesis of the HMF. Here, our consideration was not to reach a very high yield, but to get a selectivity of more than 99%. That means that all the fructose is converted in the HMF. If we try to get a higher yield, the selectivity drops because of the instability of the HMF, and you start to have quite a lot of byproducts. Since this is going to be kind of a closed loop, we were not worried to have low yields in the sense that all the things are going to be recovered in this cycle. And actually, the furans are, I think, quite an important field at this moment, because we can get quite a lot of products from the lignocellulose, and due to the instability of the furans, we cannot heat them to higher temperatures. We cannot make processes with many chemocatalysts because of the instability. We think that biocatalysis can have quite a lot of interesting things to say here. And this is a review we published some years ago, showing some of the examples that we have from this, which I mean, we can have oxidations, reductions, we can have condensations, esters, and so on. We have quite a lot of products from furan by using biocatalysis. And this is, and we did some work in the ester part. For instance, we realized that the classic CalB was able to make a esterification. This is very funny, because when we started to work on this, I told the student, make a search in the literature, because I'm sure that the esterification of the HMF with the CalB is reported. Had never been reported at the time. So, I mean, this is something that was a surprise at this moment. Many people are focusing on chiral synthesis and not in bio-based molecules. And then we realized that with the CalB, you can really make quite a lot of interesting stuff. For instance, this one, you get kind of a wax, solid wax at room temperature that is being melted at 46 degrees. Could be used for something. Or also this one, to make in solvent-free process the condensation of the methyl carbonate with HMF. We made just a proof of concept, and we realized that we can reach more than 20 grams liter of this product per hour of reaction, 90% yield. So it works quite well. Probably we can have chances to make products playing around with this molecule. And now we have a situation here in the sense that we have more or less 85–90% yield of this one, but we get 15% of the HMF still as a molecule. And we cannot make the separation of them by distillation because of the reactivity of the HMF. So we found a way to make the separation of this, which is the use of this. Because these are quite interesting in the sense that when we have a mixture of esters and alcohols, this can dissolve the alcohols but cannot dissolve the esters, which tend to form a second phase. So we can make a mixture of this test with this ester alcohol mixture. We get this separation system, we get the ester, and then we put a second solvent from which you get this alcohol to be recycled, and we can also recycle the test. We tested this with this system, and it works quite well. This is the concept, as I said before. We have the ester as a second phase. I put here the structures of the test that we use because I want you to realize this simplicity of the solvents that we are using. It's just a mixture of choline chloride and glycerol, just a mixture with xylitol, just a mixture with urea. It's not something special, it's just mixing two chemicals. And it worked quite well because we got more than 95% ester recovery in one cycle with a purity of more than 99%. So probably this can be put on a continuous mode to get the system to work. With the furans also, we can work with liases, and then we can make a condensation of the HMF to make these kind of structures, which can be used as polymers, for instance. Or we can make a blend in a mixture of the fufura and the HMF to make kind of mixtures of them. Depending on the concentrations of them, we are going to make this system. By hydrogenation of this stuff, we probably are ending up in something that could be related to jet fuels. So we get a range of alkanes that could be used also to be burned as fuels for jet fuels. And of course, once that we realize that we have a choline chloride solid, we have this stuff with free alcohols. This is solid, but we thought, okay, since we are playing now with the test system and so on, we decided to mix them to see if we could get a new DES. And in fact, when you mix these two stuff, which are very big stuff, it's a surprise, but you get the liquid. You get the new DES. It's viscous, of course, it's not like the other DES, but it's a liquid form at room temperature. Now, we don't know for this could be used, but we are quite excited in the sense that we are developing a new solvent from biogenic sources. So, and this allows me to introduce the continuation of this part, which is this interface project that we are now working. Interfaces project is a new project that we started this year, involving several partners from industry and academia. We have 40 PhD students working with this, with a very nice funding for this idea. So the PhD students are going to work part in industrial environment and part in the academia to try to have both sides of the research. And the idea is to work from bio-based monomers that we can get from biogenic sources and to make the value generation via biocatalysis. So we are going to find 3 work packages. The first one is going to design the variants that we are going to have for these processes and these supports in which these variants are going to be immobilized. Then we are going to have the assembly of this catalyst to try to work in multi-step processes. And finally, of course, since we want to show that biocatalysis can something to show in the market, our ambitious plan is to make kind of scale up to show that the productivities of these processes are in specifications for industrial cases. So for the lignin part, just some hints on that, what we did with the lignin. One research line is to work on keterases, which are enzymes that can make the oxidation of lignin. And with this system, in some works, we managed to get an oil from the lignin, which can be used for other kinds of stuff. And I'm going to show you now a concept that we found unexpectedly when we were working in lignin, which was the aromatization of lignin without the catalyst in a mixture of hydrogen peroxide and dimethyl carbonate. Lignin is aromatic, as we can see here. So we put the lignin in this mixture, and we got this white stuff from the polysaccharides, starting from wood, and this oil from the lignin. So I told the PhD students, please do an NMR of this oil to see a bit what we have. And what she showed was this spectra, which was quite strange because in the range of the aromatic rings, we didn't see a band. So I asked her, this cannot be true. We did something wrong in some place because lignin is quite aromatic. It is impossible that this oil cannot have any aromatic band. So then to test this, we make kind of a polymer that is called synthetic lignin that you can make in the lab. You can start from the coniferyl alcohol with peroxidase, with some hydrogen peroxide, and you get a polymer that is like a lignin, and we call synthetic lignin. The big advantage of this is that it's pure. You don't have impurities from sugars, from wood, because you don't put sugar in the reactor. When we did this spectra of this synthetic lignin, we in fact saw the bands in the aromatics. And when we treated this synthetic lignin to this concept, once again, we didn't see the aromatic bands. So in fact, we are the aromatizing lignin. And what we realized was that the aromatization was dependent on the amount of peroxide that we were putting, also the yield, of course, because we are breaking lignin. And we managed to get the complete the aromatized lignin, which is in the form of oil. Here, this one is already more or less in this range. It's like a chewing gum. You can really stretch it. It's very nice, and this is more solid stuff because we are in this area. And the reactions that are taking place, we believe that are these kind of processes that we have here. We are going to have an oxidation of the aromatic rings, and then at the end open it and then get the aromatization pattern. But the interesting point is that we can get some products, not one lignin, but some products that can be used in some markets, depending on the properties of each one.
Also, the synthetic lignin was quite interesting to be used to search for new microorganisms that can work on lignin. So we don't have impurities of sugars if we use a real lignin. So we did an experiment. We took a soil sample and we did the screening with lignin as a solid carbon source. One part of the soil with Organocat lignin, another one with the synthetic lignin. And the good news was that we found the same kind of organisms in both cases. So we can cheat the nature, we can screen soil samples with the synthetic lignin that is, you can make it in the lab and you know it is completely pure for that. So now I have been talking too much and I think the time is finishing. So now I guess the investor is coming from the door and he's going to ask only one question. And the question that he's going to ask is, what have you done with my money? That's an important question here. So we need to show him what we did or what we can put forth for this. So the first step that we are going to make is in pretreatment, is the entry of a biorefinery. We get the lignocellulose, we make in one step 100% biogenic. We get the lignin, the hemicellulose sugars, and the cellulose pulp. With this, I think we could even stop and say, okay, these three fractions have already market, so you can start to play around. But since we want to differentiate from other biorefineries, we did other things. With the lignin, we started to work and we get different kinds of the aromatized lignins, which can be used for some kind of markets, for coatings, for paintings, for passive lubricant. We don't know yet. With the cellulose, we put in combination with iron chloride, and we get the fufura, which has already market price. With the cellulose pulp, we put it in seawater, or you can put it in other kind of residual water that is not used for human use. And we, in contact with the cellulases, we can make the glucose, which we can make in contact of the glucose isomerase to make the HMF stuff. So we have some valuable things from there. And from this, we can make the esters, which can be make a valorization as a surfactants, as additives for many type of applications. We can also make condensation of this to make kind of monomers for polymers, and many other things that we can envisage from this. So starting from 1 kilo of lignocellulose, what we can put forth now to the investor is you have a process to make separation, and you have quite a lot of leads that now we need to explore for the developing of a business, of a market, and to look for kind of places to use for this material. So with this, I would like to give the credit to quite a lot of people, because it's a project of 10 years now at this moment. I'm working in different places with different people. So of course, I want to give the credit to all these persons that are here, and also the agents that gave the funding for these projects. And I would like to thank you for attending the meeting, for your attention. And if you have any questions, I will be very happy to try to answer them. Thank you very much.